Next, I'd like to introduce Yilun Zhou. He's going to talk about representing and learning complex object interactions.
So good afternoon, everyone. I'm Yilun Zhou, undergrad rising senior from Duke University. Today, I'm going to present my research joint work with my advisor, George Konidaris, on representing and learning complex object interactions. So there has been excellent progress in directly manipulating a single object. However, many tasks involve indirect interactions of some objects through others. How to represent and learn such tasks is the focus of our work. So first, imagine teaching a robot to drive a car. The ultimate goal is to move the car along a desired path. However, controlling the car can only be achieved by manipulating the steering wheel. Nevertheless, simply recording a demonstrated steering wheel trajectory does not actually learn the task of driving the car to follow different paths. Thus, in this task, as we can see, the steering wheel acts as an intermediate object between the robot and the car. The robot controls the steering wheel, and the steering wheel controls the car. To represent this task, we propose an interaction chain structure. In this representation, each object, including the robot, is modeled by a Markov decision process. These Markov decision processes are coupled together by having the state of the predecessor object being the action of the successor object. So here, the robot hand position becomes the action of the steering wheel by changing its rotation angle. The steering wheel rotation angle becomes the action of the car by changing its position and orientation. Then to control the car to follow a specific trajectory, we recursively use inverse transition functions, which for each interaction map a transition of the successor object to the action of the successor object, which is by definition the state of the predecessor object. In this example, if we know how the car should move, we can determine the steering wheel rotation angle that can induce the car movement. Then the robot can move its hand to rotate the steering wheel in the desired way. And then in the experiment, the robot needs to use a joystick to control a car in a computer game. As we can see, it learns how to use a joystick by physically playing with it, and learns how the joystick controls the car by watching a human to play the game. Then in the execution, the robot needs to use the learned inverse transition functions to control the car through several challenging paths. As we can see, all paths are followed very closely. Although the above example can be described as an interaction chain, more complex tasks do not have chain-like interaction structures. Thus, we extend the interaction chain to interaction graph. For a specific example, consider using a water dispenser to heat a cup of water. In this scenario, there's a cup, and the water dispenser has a power button, a dispense button, and a water tank. And here's the interaction graph. The robot can press the power button and the dispense button. The robot can also move the cup. The power button interacts with the water tank by heating the water inside the water tank, and the dispense button interacts with the water tank by emptying the water tank. The cup can pour water into the water tank, and the water tank can dispense water into the cup. We know that not all interactions are active at all times. So for example, when the robot is pressing the power button to heat the water inside the water tank, other interactions are not active. Thus, we associate each interaction with activation and deactivation classifiers to describe conditions on which the interaction becomes active or inactive. These classifiers simplify learning and control by inducing a smaller active subgraph within the whole interaction graph at all times. In the experiment, the robot is teleoperated through several separate skill trajectories, such as pressing buttons and pouring water. Note that these skills are provided without specific order. And then in the execution, the robot needs to turn a cup of cold water on table to a cup of hot water on table. With the provided interaction graph, it can autonomously select and sequence relevant skills for a full control trajectory. In conclusion, we propose a framework to represent complex object interactions. The biggest advantage is modularity because each interaction can be learned separately and in respective reference frame. In addition, the modularity enables transfer of knowledge by using an already learned or provided interaction rather than learning the interaction from scratch. Thank you for watching, and if you have questions or want to know more about the research, I'll be happy to talk to you at poster podium number 39.